3 neurons. So I created a small example for you guys. I'll give you all the code. You will go home, play with it. But this way you will have a very, very nice feel for what do the hidden layer neurons do. Okay. So let me show it to you. Okay, and I'm comparing it with logistic regression. So don't worry, I'll give you the code. Right now, what I'd like you to do is just take a look at the results and be able to understand it nicely. So anyway, I wrote the same code that we have for logistic regression. So you can see I create one object of the logistic regression over here, right? So there's a class called logistic reg. Okay, inside it I have a function to initialize the data, random data, but such that the decision boundary is nonlinear between the two, right? So then I train it and try to plot the decision boundary. So let's see if you can recognize it right away. So this is the data. As you can see, there's no straight line that will classify. The logistic regression will try to do as good of a job as it can, right? So once I close it.
Yeah, you have R instead of R. So in R, the train should be LR.
Let me run it again. So that's the original data. Now it will train and it will create the decision boundary. Okay. So this is the best you'll see. Some of the red ones are being put in the blue, right? And even though you cannot see, there are dark red ones over here which are correctly being classified. The blue ones are obviously incorrectly being classified, right? How's the decision boundary? Is it a straight line? And we all know logistic regression creates a hyperplane separating the two classes of data, right? So this is easy. Okay. And by the way, the accuracy was 85%. It's hard for you to read. So 85% of the data I correctly classified, whether it was red or blue. Okay. Now let's go and remove the logistic regression. So I'll use this exact same data. Now I created a neural network, very simple neural network. I'll show you the code in a second for the neural network, and create and test the neural network. X is the input data, Y is the predicted class, and this 5 is the number of neurons in the hidden layer. So if I pick 1 in the hidden layer, what would you expect the decision boundary to be? Straight line. Okay. So if we go, so it's training the neural network. And do you see it's straight line? And the accuracy, it's very similar to logistic regression, except as we discussed, the loss function is different. So the 0.865, the other was 85%, this is 86.5, so fairly close. Okay, now let's go increase the number of hidden layer neurons to 2. So now what would you expect? Bunch of curves or just one smooth curve? So let's run it. So again, same data. So it trains the neural network. So you can see it created, you know, a little bit like this. Still a lot of inaccurate classification. Let's see, 84.5%. So it didn't improve a whole lot, right? Let's make it 3 neurons. So now you can see we'll create a couple of curves, right? Okay, so does that seem reasonable, right? Is it better than before now? You can even visually see just a 1 or 2 red or blue have been incorrectly classified, right? So 97.5% accuracy, right? So now I have an important question for you guys to answer. If I make it 4, will the accuracy become better?
Not necessarily.
Okay. What if I make it 100?
It will be on the test data, it will be.
That's the correct answer. On the test data, we'll do a fantastic job. Okay, but if somebody gave it unknown point, I'll show you in a second, then it may not do as good of a job, right? So anyway, let me just go to 5 as an example, rather than trying each and every number. So this is with a hidden layer of size 5. Okay, so did you see it created another island over here? So is that good or is that bad?
Bad.
Why is it bad?
Because it's really tailored to that one.
So now essentially what it's trying to do is it's trying to tailor this particular data exactly. See, in reality, we may not have a shape like this. It may be a smooth shape over here. Of course, we have noise in the data, so we don't want to take care of each and every noisy data. So this concept is referred to as overfitting. So overfitting is a fundamental problem in deep learning. Okay, whatever model we want to create should be such that it represents the data as nicely as possible without trying to tailor to this particular data. So we wanted to tailor to the shape of the data, but not each and every data point over here. Okay, so as you can see, this clearly, by this little peak over here, this part over here, it's simply overfitting the data. So for this particular problem, my question is, what will be the best model? Model is same as architecture. So input, we don't have control over. It's a two-dimensional data. There will always be 2 inputs, right? Number of hidden layer neurons, we have control over. We don't have control over the output layer as well because it's a binary classification. So there will be either a single neuron or 2 neurons. Okay, so this is what you are controlling, essentially, number of hidden layer neurons. So what's the best model?
How long would you try?
The one we have tried?
3.
3. And 4 and onwards, you'll see it will start to overfit the data, right? So for example, just out of curiosity, let me just put 20 over here. So I way overfit the data. Yeah, it's slower because it has to compute quite a few gradients and updates. Okay, so anyway, this is with 20 neurons. even though on this data will be pretty high accuracy, 99% accuracy, okay, missed only 1 point, but that is not a good model, okay. So we want, whenever we want to create an architecture, we want to do it such that we prevent overfitting, right? Okay, so I'll go over some of the techniques that we use to prevent overfitting. And then I'll also talk about, so far we have talked about binary classification. Okay, what if we have more than one class? Then what is the best technique for multi-class classification? Okay, so let me go back to the board. Okay. Okay, so techniques to prevent. So there are several techniques that we employ. Okay, one of them is called weight beating. Okay, so here the idea is like this. Smaller weights tend to be better. Meaning if we have weights in our network which are relatively larger size, will cause rapid fluctuation in the output and also will give us overfitting. So the questions, so essentially what we want to do is we want to design the network okay, such that magnitude of weights is as small as possible. Okay, so what we do is we incorporate this in the loss function. Okay, so our typical loss function for a neural network, as we have discussed, would be, for example, I equal to 0 to m ai minus yi squared, correct? So then what we'll also do is we will also try to, whatever the weights are, we will also try to put that term over here, because remember our goal is to maximize the loss or minimize the loss? Minimize the loss. So if we are trying to minimize this term, as you can see automatically there are two components to it, right? This is the expected output. This is the actual output. So we are saying actual should be as close to the expected. If we're doing a classification, that's pretty natural, right? And further, so this alone is not enough. Further, what will happen if the total magnitude of the weights is pretty high?
Loss is high.
Loss is high. So we'll automatically try to pick those weights where the loss is as small as possible, right? And again, as I mentioned, to make the partial L over partial W come out as nice as possible, we typically add the half term over here, half term over here, right? Okay. Now, sometimes what we want is we want to have them be proportional to each other. But, sorry, not proportional to each other, but we want, if we emphasize this part too much, right, then you can see it may not do as good of a job with the classification, and vice versa, right? Maybe it's doing a good job, but the weights are higher, relatively speaking. So typically what we do is we also add a parameter over here, lambda over here. and we control the lambda. For example, if we put e.g., if we put lambda equal to 0.01 as an example, so you can see it is going to focus more over here, right? But a small part of it, maybe 1% of it will try to also make the weights as less as possible, right? Okay, so what does that do to the loss, to the partial L over partial W, as you can see? What does it do? As you can see, if I take the derivative with respect to W, what will this be?
Just wait.
It will be just W, right? Plus whatever the derivative is because of the first term. Okay, so once I try to adjust the W minus alpha, right? And then gradient of
But we have
whatever.
lambda there, right? It's not a big.
With lambda weight.
Oh yeah, plus lambda. Yeah, lambda over here. Okay. So anyway, as I plug this part over here, you can see essentially there's a minus sign over here, right? So essentially what we are doing is minus lambda times W. In addition, additional term gets involved over here, which reduces the weights, right? So that's the net effect. So this is one way to prevent overfitting, okay? Obviously, this will still not do a better job if we already picked 100 neurons in the hidden layer in our last example. So if your number of neurons are reasonably close, maybe it's 4 or 5, then further adding the weight decay will not overfit the data. Okay.
A is actually a function of W, right?
A is a function of W, correct.
So rather than adding it to the weights, we can multiply it, right? Even you can reduce it overall.
Because this we want the derivatives, we already are pretty good at computing the chain of derivatives over here, right? So adding another, complicating it further is not worth it. So keep it separate term, and like I said, the net effect of this is simply subtraction by the minus, and it comes out a very clean answer, which is very easy to take care of the overfitting. Okay, so that was one of the techniques to prevent overfitting. Okay. There are a few other techniques that gradually you will use. Okay. So first of all, overfitting can be due to a complex model. I should say a more complex model over here. So again, what do I mean by it? In our example that I showed you, instead of using 3 neurons in the hidden layer, if somebody is using 10 neurons, the model is too complex, right? So we already discussed, so e.g. using 10 neurons in the hidden layer. In our example. In some other example, 10 would be needed, right? So, but I'm referring to the example I showed you on my computer. Okay. By the way, in the example that I showed you, what if we use 2 neurons? Will it overfit the data? It will underfit the data. So we do not want underfitting also. Okay. So anyway, overfitting can be due to a complex model, right? One more point over here. Overfitting can also be due to overtraining. and let me clarify this. If we train the data too much, even though the model is not that complex, it will still overfit. So our typical our typical training code goes like this in pseudo form. Initialize weights and biases randomly. And we typically pick a small number. Okay. Then we go into for I equal to 0. I'm just writing a pseudocode to number of epochs. Okay, so epoch is a term that we use where we repeatedly feed the set of data. So one epoch is one set of data. Okay, so again, our typical training code goes like this. So we may decide epoch, for example, could be 100. So go 100 times, right? And then we pick a training sample. Feed it to the network. Okay, so this is called the forward pass. Okay, so once we feed it to the network, as you can see, the actual outputs will be computed in each and every neuron. Okay, so then what do we do after we have fed one sample and we know each and every output? Then compute partial L over partial W, partial L over partial bias, and then do W equal to W minus alpha. Partial L over partial W, B equal to B minus alpha partial L over partial W. So this is our typical training code. Of course, if you have a single weight, there will be, single neuron, there will be a single weight, single bias. If you have 100 neurons, if you use the matrix form, then these will be matrices or vectors, right? Okay. So
is it like, for example, you're cleaning the data at the beginning, some kind of removing outbounded data?
So far, think of it this way. Only thing we do to the input data will be to scale it between 0 and 1. Other than that, no cleaning of the data. Once we go to natural language processing, then we do remove the periods and the other simple words like the and so on. But for classification type of data, other than converting it to numbers, we don't do anything. Okay, so coming back to what can overfit. If we train it too many times, okay, suppose rather than 100 epochs, we made it 10,000 epochs. So we're repeating this loop 10,000 times, right? So again, what we will try to do is we will try to remember the data, and you can, once you go home and I give you the code, you can play with it and you'll see, in fact, that is happening, right? So the question is, how do we safeguard against it, okay? So what was the safeguard against this technique? weight decay was so one solution was weight decay, right? If we were to add weight decay over here, then what will happen over here? This will become minus lambda times W, right? So basically, this is what will happen. Very similar to the bias, it will also become lambda V. If we were to add the weight, the term is called weight decay, but also it applies to the bias, okay? So anyway, so that was one type of overfitting. Second type of overfitting was we train too much, okay? So remember, in both cases, if we are doing the overfitting, your accuracy will actually improve. So you might say, oh, so that's why what we do is we typically have a training set and we have a test set. So to give you an example, the MNIST data that you are going to be working in assignment 3, in the MNIST data, there are 60,000 training samples. There are 10,000 training test samples. So how would we know that we are overfitting as a result of training, right?
It will do great on training.
So for example, we run it through 100 epochs. We stop. We test it. Suppose we get 95% accuracy, right? Now we run it through 1,000 epochs and we test it. If it is giving us 92% accuracy, what does that mean? Overfitting due to overtraining. Okay. So is there an quick, easy way to have us know do not overtrain or stop at this time? Okay. So typically this is what we do. So in this solution to this technique is validation set. Okay, so for example, what we can do over here is, out of these 60,000 training data, let's use 10,000, so let's use 50,000 for training, and 10,000 for validation. So what we'll do is we'll train it on 50,000. Every epoch will compute the accuracy on the validation set. Okay? So if we plot this accuracy, so this is after every epoch. Okay, what kind of graph will we expect? See if I draw it somewhere here.
It should increase and then it should decrease at a point. What's the latest?
So this is the number of epochs, right? Let's say this is the validation accuracy. Okay. So in the beginning, of course, the accuracy will be low, right? So as time goes by, eventually will start to drop again, correct? So perhaps, let's say over here is, let's say 95, 96%. So typically what we do is, once the accuracy has reached the peak for consecutively 3 or 4 epochs, because it is possible accuracy goes up, then goes down, then goes up, then goes up, right? So we don't want to stop as soon as it starts to go down. So we typically play with 4 or 5 epochs If it is still not it's starting to go down, then stop. So this is where we'll stop training. And then we will test it on the test set to see did it improve it or not, right? Okay, so that is one technique for preventing overfitting due to overtraining. Okay, let me give you one more technique that you will try in your next assignment. Okay, an easy technique and also very effective. Technique for preventing overfitting is dropout. So let me explain the concept of the dropout. Okay, suppose we have some network we created. Okay, and suppose there's some weight matrix, some neurons over here. Another weight matrix, so let's call it W1, W2, another set of neurons, and then the other. So suppose we created a two-layer network, so these are the matrices. This is the hidden layer neurons, this is the output layer neurons. Okay, and as I discussed, depending on the data, a certain size of the hidden layer neurons will be optimal. If we pick too few, what will it do? Underfit. If we pick too many, what will it do? Overfit the data, right? So typically what we'll do is we will pick more neurons, we'll estimate and we'll pick more so that it does overfit. Then we'll counter the overfitting by using dropout. Okay, so what exactly is a dropout? Okay, so first of all, dropout only used in input and hidden layers, not in output layers. Okay, so we never use them. And think of dropout as a separate layer. Easy way to understand it is it's a separate layer. Okay, and all it does it simply either zeroes out